So for today, we're looking at 9.3, day 1. So now we're going to move on to confidence intervals for a sample mean. So in 9.2, we were always doing proportions. Today, we're going to look at means. A lot of the setup is the same except for two things, really. So remember, first thing we always want to do is list our conditions. So these are really our conditions. So the first one, just like with proportion, is you want x bar, the sample mean, from a simple random sample or some sort of random sample. One difference here is condition 2. Either the central limit theorem applies and the sample size is large, so n is greater or equal to 30. So then we could say, therefore, our sampling distribution is approximately normal by the central limit theorem. Or sometimes they'll just tell you the population distribution is already normal, like an SAT score, that kind of stuff, weight, height. This is different than a proportion. A proportion doesn't have this. It has to do the central limit theorem only. So that is one slight difference with a mean. And then we're going to figure out if the population standard deviation is known versus is it not. So 3 is usually, we're going to do one sample z interval for a mean. Oops, sorry. So one sample, remember this is always defining what interval you're doing. So we're going to do a one sample z interval for mu because we're going to know the population standard deviation. Then 4 is always to define our parameter. So this time with a mean you want to use mu. So mu equals the true mean whatever. Now, if you get your purple sheets out, again, it's the same, right? Statement about simple random sample, normality, give the confidence interval a name, describe your parameter. So that's our first conditions. Your testing here, here's your formula. So the things you have to give me, you have to give me x bar, you have to give me mean, you have to give me n, and you have to give me the z critical value. This is on your formula sheet. If you along with the proportion one, kind of off to the side up here. So to figure out the standard deviation, it is here. So you don't have to memorize these. And they're from chapter 8. So remember your confidence interval down here is the statistic, so either p hat or x bar, plus or minus your critical value, times your standard deviation, which will either be this or this. So both 9.1 and 9.2, the formula sheet has the formula if you know where to find it. So you don't necessarily have to memorize this. Okay, so let's try one. So a certain filling machine has the true population standard deviation of 0.228 ounces when used to fill ketchup bottles. In a random sample of 36 6-ounce bottles of ketchup was selected from the output of this machine, and the mean sample was 6.018 ounces. Find a 90% confidence interval estimate for the true mean value of ketchup from this machine. So again, the first thing you want to do is write out your conditions. Okay, so the first one is it's a random sample. Right here, random sample 36. So x bar is from a random sample. So we're good there. Now, check your central limit theorem. It doesn't say it's a normal distribution to start, but 36 is greater than 30. Therefore, our sampling distribution is approximately normal by the central limit theorem. 3, we know the population standard deviation. Tomorrow we'll get to what happens when you don't. So we're going to do a one sample z interval for mean, so for mu. And then our parameter, mu is the true mean weight of bottles of ketchup. So there are your conditions. So make sure you have those. Now we're going to do our testing. So always give me the pertinent information. So we know n is 36. We know x bar is 6.018. Sigma was 0.228. A 90% confidence interval gives us a z critical value of, now if you can't remember it, you can always look it up, but it's 1.645. Oops, can't see that. So list the information, write your sentence about our z star, then plug in the formula. So it's 6.018 plus or minus 1.645 times 0.228 divided by the square root of 36. Now, you can do that in your calculator if you want, or, again, this is in the calculator. If you get your calculators out, go to Stat, go over to Test. This is at what we call a Z interval. So it's test 7, Z interval. So Z interval. So if I plug that in, now it's going to say data or stats. Data would be if I gave you like each of the 36 out, like, and you put it in list 1. We want the stats. So first thing it's going to ask you is for the population standard deviation. So 0.228 x bar. So the nice thing about this is it kind of helps you figure out what do I need to give you, what's that pertinent information. It's everything that you're putting in the calculator basically. And then we're doing a 90% confidence interval. Then you hit calculate. So it's between 5.9. And you can just keep going or round to whatever you want. I would say at least 2 decimal places. And then write your conclusion. Now the only thing different with this conclusion is you're going to have to include units, which is ounces, I think. So we are 90% confident that the true mean weight of bottles of ketchup from this machine is between 5.9555 and 6.0805 ounces. So the only thing that's different that you need to include for the conclusion is make sure you include units now. Okay. So then that's your Z interval. So everything for Z interval looks like that. Again, 4 points, 4 points, 2 points normally. So all of this only works, we can go backwards too, just like we did in 9.2. On the back, we can also find the sample size. So suppose we wanted to estimate the average height of a Salem student within 0.5 inches of the true value with 99% confidence. So we can use our formula that we had from 9.2. But this time standard deviation is different. Remember, it's B is equal to your Z critical value, but this time it's times sigma divided by the square root of n. The good thing about these kinds of questions with a mean is I have to give you sigma and B. There's no, like, with a proportion you could assume it was 0.5. Here you can't. I have to give you those 2 pieces of information, which is what I did here. So here's the standard deviation. Here's what we want ours to be. Let's figure out what sample we need. So go backwards. There's not a lot of room to write it, but 0.5 equals, now we're 99% confident we need a Z critical value, which from the other day 0.92 day 1 is 2.575. Again, if you look up 0.995, you'll get it. So 2.576 times 2.3 divided by the square root of n. Okay, so you gotta write kind of small. Focus it more there. So first thing I'm going to do is divide. So 0.5 divided by 2.576. Oops. .194 equals 2.3 divided by the square root of n. Think about this as a proportion where you would cross multiply. You get 2.3 equals 0.194 times the square root of n. So I'm going to divide again. So I'm going to take 2.3 and I'm going to divide it by my answer here. So 11.8496 equals the square root of n. And then I'm going to square both sides. So n is 140.41. Just like we did in 9.2, round up. So what should my sample size be? I should pick 141 students. 141. So just like we did in 9.2, but with means. Unfortunately, the problem is with what we just did, we rarely, if ever, know the true standard deviation and not the true mean. So these problems are somewhat unrealistic. So in most cases, to find an appropriate sample size, first we need to estimate the standard deviation. There are a few ways to do this. We can either use a previously known value for S, the sample. Remember, that's your sample standard deviation. Or you can do a preliminary study and use the sample standard deviation S. So the thing is, with this, you can't use the Z distribution. So we're going to use these things called a T distribution. If X is a normal distribution with a random variable, the T test statistic uses the sample standard deviation and follows a T distribution with degrees of freedom, that DF that I've been saying ignore, of n minus 1. So kind of what happens, it's kind of hard to see with this one because it's not colored, but this top one is a normal distribution. Bottom one is degrees of freedom of 2. So the more degrees of freedom you have, the higher your sample size, the closer you get to a normal curve. Because the problem is we're just estimating the true standard deviation from the sample. So we got to give ourselves a little bit of leeway. But the more our sample size increases, because we're only subtracting 1, the closer we get to that normal distribution. So as degrees of freedom n minus 1 increases, the T distributions approach the normal curve. So since a T distribution would require a table similar to the standard normal table, we usually only create a table of critical values for the T distribution. So we're going to work on this tomorrow. Instead of using a Z interval, we'll do a T interval. Okay, and we use a different T critical value. On your formula sheet, that third page, and we'll talk about it tomorrow, is the T distribution. So if you notice what happens, the bigger your sample size is, the closer you get to our actual Z critical values, which end up being down here if I haven't pointed that out yet. Like a 95% confidence interval, that's our Z critical value. So we'll talk about this more tomorrow. But just know that third page of your formula sheet is going to come in handy.